and this is Lab 4 on 2D spring mass oscillations for Physics 2211. In this lab, I analyzed the motion of a two-dimensional spring mass system using video tracking software called Tracker. I then compared that experimental data to a computational model created in GlowScript, and then I finally used energy graphs from the model to verify whether energy is conserved in the system. So this lab is based on Newton's second law and the energy principle. Newton's second law states that the net force on the object equals mass times acceleration. In this system, the net force is the sum of the spring force and the gravity. The spring force follows Hooke's law, which depends on how much the spring is stretched from its relaxed length and acts in the opposite direction. And then gravity obviously acts downward. And then for the energy, the total energy is the sum of the kinetic, gravitational, and spring potential energy. And if the system is isolated, the total energy should remain constant over time. And the model updates motion using numerical versions of velocity and position equations at each time step. And here are the equations on the side right here. So using Tracker, I analyzed the motion frame by frame to get position data. The mass of the object was approximately 0.2 kilograms with initial position of negative 0.122 in the x direction and negative 0.617 meters in the y direction. And it had an initial velocity of 0. So from this, I extracted the x and y positions versus time. And the motion appears smooth over here and periodic, which is consistent with oscillatory motion. So these graphs show the experimental position data, which was in the tracker. So both the x and y positions follow a sinusoidal pattern indicating oscillation. And the period is approximately 1.3 seconds and is consistent in both directions. And this confirms that the system behaves like a spring mass oscillator. So in the computational model, I use the same initial conditions from the experimental data as shown right here. And the model includes both gravity and the spring force, obviously. And the spring constant was set to about 12 newtons per meter, and the relaxed length was about 0.12 meters. And these values were chosen to best match the observed motion from the experiment. So in this part of the code, the physics of the system is implemented. So here the net force is calculated as the sum of the spring force and the gravity. And the spring force is calculated using Hooke's law based on how much the spring is stretched and its direction. And then Newton's second law is applied to update the velocity and position step by step using small time intervals. And this process is repeated continuously to simulate the motion of time. Like this is like a while statement. So when the time is less than 5.5 seconds, this code is going to keep on repeating itself. So this model also calculates the energy at each step. So the kinetic energy depends on the velocity, the gravitational potential energy depends on the height, and the spring potential energy depends on the stretch of the spring. So the total energy is the sum of all these three energies. And these calculations allow to test whether energy is conserved in the system. So here's the model versus data graph, and these graphs compare the computational model to the experimental data. And overall, the model closely matches the experimental motion, especially in frequency. Obviously, there's going to be small differences in phase and amplitude, and these differences are likely due to measurement error and simplifications in the model. So here this graph shows the change in energy over time. It shows the kinetic, gravitational, and spring energy all oscillate as the system moves, transferring energy between the forms. But the total energy remains approximately constant, confirming that the energy principle is satisfied in this model. So some possible sources of error include that the tracker may not have perfectly followed the exact center of mass. Air resistance and friction were not included in the model. Also, the spring was assumed to be very ideal, which is not perfectly realistic. Um, and also the numerical time step and introduces small computational errors. So, in conclusion, the computational model successfully represented the experimental motion, and there's a strong agreement in frequency and overall behavior. And also, the energy conservation is clearly demonstrated. Um, And lastly, the small differences between the model and the data are expected and can be explained by experimental and modeling limitations. Thank you.